So deflection of beams and frames. You guys remember last time the methods that we can use to calculate deflections on beams and frames? I got a bunch of them and I said that we are going to study some and some we're not going to cover. So the one that we are going to study is double integration method. And number 2, conjugate beam. And also there's other methods like the elastic load method or the moment area method, but these are the 2 methods that we are going to cover. And as we said last time, studying deflection is like you are having a beam like something like this, and there's a load beam. This load beam triggers stresses, and stresses triggers strains, and strains triggers deflection. Okay, load, stress, strain, deflection. And what we are interested in, we need to find what is the deflections in the beam. All right, so we are going to start with the double integration method, number 1. Double integration method. And from the name of the method that it has integration. I hope that you guys still remember how to integrate functions, okay? All right, so double integration method is a procedure that establishes the equation of the elastic curve of a beam. Like if you have, for example, if you have a beam like this, and there is a load like that, we need to establish an equation that can describe the elastic curve of the beam. Elastic curve means the deflection curve. How does the deflection look like? Do you have a question? So this is the elastic curve of a beam. There's other equation that doesn't establish the equation of this curve. It's just to calculate the deflection at a specific point. But this one is much more general because it gives you the equation of the whole curve. You just substitute where you wanted to calculate the deflection at x. So get me, and I substitute at x and get the value. Okay, so that's a very general equation. All right, let's see how we can do this. I started this last time. So let's take this example, like the cantilever example. All right, so if I have cantilever like this, and there is a load beam like that. This beam, we know how's the deflection look like. We know there's a fixation. The fixation doesn't allow deflection. And also, okay, I'm gonna ask you, this is how the deflected shape look like for a cantilever. What is the amount of deflection here?
0.
What is the amount of slope?
0.
0. So slope and deflection are equal to 0. All right. So what I want to know, like if I know it here, but I don't know it somewhere else. Like what if I want to know the slope and the deflection here at point A? That's what the double integration method is going to tell us. So to do this, we are gonna I'm gonna go through bunch of equations, doing like bunch of stuff for like half an hour to come up with one equation, which is the most important equation for the double integration method. This equation you should have it, you should remind it, should be in your head all the time because that's a very, very important equation for a structural engineer. This equation it says that the moment is equal to EI multiplied by the second derivative of the deflection with respect to x. This is very, very important equation. If you are going for your BE exam, I'm not sure, maybe also the FAE exam, this is very important equation. What is y? The y is the amount of deflection that you have. If you have a beam like this, and this is the deflection, the deflected shape, this is y. X is the distance from the support. So the second derivative of y with respect to x squared multiplied by EI is equal to the bending moment. So that's the relationship between moment, internal forces, and what we call this is the curvature, d square y dx square. So there is three components related to deformations. Like there's three components, the same way that we have components related to internal forces like normal, shear, moment, and maybe torsion. Torsion is a type of moment. So we have these variables or these internal forces. Also the deflection has something that we can describe it with. We can describe the deformation, not the deflection, the deformation with three different types: y, theta, xc. Y is called deflection, and that's very obvious, which is the distance from the non-deflected line to the deflected line. Theta is the slope, which is like you draw a line like this at any point. Like if you wanna find the slope here, you draw a line here and you measure from the horizontal. That's the slope. Or it's the change in y with respect to x, dy dx. Xc is the curvature, which is the change in the slope with respect to x. Alright? So you have y. If you differentiate y with respect to x, you get theta. If you differentiate theta with respect to x, you get xc, which is the curvature. That's the three variables that we are interested in. How we can find them, we will do it now. Alright, so to find this, I'm gonna take a very, very small, infinitesimal distance in the cantilever. It has a point A and an end at point B. And this distance is very, very small. A at a distance, arbitrary distance x, and B, it is at dx from A. Very, very small distance, okay? So let's take this out and study it. So when a beam starts to have a deflection, it's gonna be like a curve, and this curve is a part of a circle. And to find the center of this circle, okay, let's get AB here. This is A, and this is B. To find the circle that A and B part of, you draw a perpendicular and another one until you go to the other point. Okay, and this is the center of the circle that AB is a part of. All right, and we call the radius rho of this circle. Okay, all right. So the slope at point A, basically you draw a horizontal and you make a one that are tangent at A, and this is theta. And you can do another one at B, and the difference between the two angles is d theta. Same thing here, like if you draw like a line horizontal and one at A, and you can make another one at B. So this is theta, which is the slope at A, d theta, which is the difference between the slope at A and B. A and B. This is d theta. All right. Okay. The length of the beam here, this length is ds. But the horizontal projection of this distance is dx, and the vertical projection is dy. In between them is ds. However, dy is very, very small. Like, can you imagine you have a 5-meter cantilever or a 3-meter cantilever and has 2 millimeter deflection, and we take as very, like the total deflection here. So how about if I take infinitesimal area, infinitesimal distance? How much is the deflection here? It's gonna be very, very small. dy is very small. So we can assume that dx is almost equal to ds. That's a valid assumption here because they are very, very small distances. Because dy is way smaller than dx. Even dx is a very, very small, but dy is way smaller. Okay, so that's one of the assumptions. All right, so, and the angle here, as we agreed last time, that's the angle theta. Like if I got here and this distance is dy and this distance is dx and the angle this is theta, so you can say that tan theta is equal to dy over dx. And from the geometry of small angles, the geometry for small angles, it says that if theta is small, tan theta is equal to theta, also equal to sine theta, equal to tan theta. All right, so right now, if I have y as a deflection, if you want to get the slope theta, that's dy dx. So I know that as well. Let's find out how we can get xc. Xc, we can get it by the relationship between rho and ds. Like, I know that this angle is d theta, which is the difference in the slope between a and b. And we said last time that if we want to find the value of ds is equal to rho d theta. Do you guys remember? Mm-hmm. Because it's a part of a curve, and if we want to find a part of a curve, we multiply r by the angle corresponding to this curve, like the same way that we have a circle, and this circle is 2 pi. So if you want to find the perimeter, it's 2 pi r. If you want to find just quarter of a circle, so it's going to be, this is 90 degree. 90 degree is pi over 2 and multiplied by r. If you find this part, you need to find that theta in radian and multiply it by r. Is going to give you this part. Same thing here, ds. And we said that ds is almost equal to dx. So we can say that this is equal to dx. So if we want to find d theta by dx, so it's going to be equal 1 over rho. And we said that d theta by dx is the curvature. That is xc. So right now we have the three quantities, y and theta and xc. The deflection, slope, and curvature. That's the three quantities that we need. Let's box them. So you have, this is very important equation. Also, this equal to, if you differentiate d theta dx, what is the value of theta? It's dy dx. So if I got d dx of dy dx, what is this equal to? D dx of theta, and theta is dy dx. What is going to be? The second derivative of y with respect to x, d squared y dx squared. Do you guys remember this stuff? Second derivative, okay? If I want to take d dx for this, it's going to be d cubed y over dx cubed, right? Okay, so that is the part of calculating the deflection. So let's get to another part. Let's dive in deep into the stresses and the strains that happen at this cross section. Right now, all what I got, deflection, slope, and curvature. All right? So let me write here differential equation of elastic curve. Differential equation of the elastic curve. All right, let's say that I have a beam like this, any general beam, like simple beam. And there is a load like this, for example, something like that. Or any general load, something like this. And this beam is going to have a bending moment, something, let's say like this, all right? And I take a cut in this beam. Oh, how's the deformity of this beam look like? So this beam, since the loads all goes down, so it's gonna be something, for example, like this. Once it's deformed. All right? So let's take a section in this beam and see what's going on in this cross section. Like, let's cut something here. So this is the moment at this section. And this is the point that I'm looking at. So undeformed shape is gonna be like, this section is gonna be like this. Once you put the load, this is gonna be something, for example, like this, and something like this. So it's gonna be compressed from the top and tension from the down, so the cross section is gonna be something like this. And if you wanna find the radius, you like extend the line like this, and line like this until you find the center, and this is d theta. But let's actually take this section out, like take a very, very small infinitesimal area or cross section like here, and has a value dx, and dig deep into it. Like if I take this out and I make it bigger here, and look what is gonna happen. This section, when I cut into it, it's gonna be something, let me draw. So what you have is gonna be a bending moment like this. Why? Because this beam has the loads, all the loads is going down, so this cross section is gonna make like this, so all the bending moment is like this. It compress the top part and make a tension down. So we have tension down, compression on the top. All right, so let's get in the middle here. Assuming that the top part is gonna have compression, I mean like the half of the beam, but it's not necessary to be half, maybe just a little bit, maybe it depends on how's the moment look like, but I'm gonna assume it's gonna be something like this. I wanna draw the stress and the strain, how it's gonna look like. Let's put here stress and the strain. So I'm gonna make a line that's gonna show how's the stress and strain look like. So for the stresses, I know that the top part has compression, so it's gonna be something like this, like stresses, and the maximum compression is gonna be top, and the maximum tension is gonna be down, and in the middle, there is no tension or compression, there's zero, right? Okay, so here you have compression, it's compressed this section, and here you are gonna have, it's compression, right? Yeah, the moment, and then you're gonna have this as tension, something like this, and this is the sigma. The strain, you're gonna have compression strain up there, epsilon, and here you'll have negative epsilon, something like this. And this angle is gonna be equal to d theta. Like look at this cross section, like if you take it here, and this one is gonna have compression like this. So it's gonna be, this cross section is gonna be something like this. This is gonna be pushed this way, like here. This is gonna go this way, and this is gonna go this way, and that's what happened here. That's moved this way, and that's moved this way. All right? So you are gonna have this until you come to the neutral line, and then it's gonna be tension or elongation. Like here is compression, and let's say that the compression is DL, like this section went DL this way and negative DL the other way, all right? And let's assume that the distance from this neutral line to the top is C, okay? All right, and definitely the angle here is d theta, which is how's this section, the difference between this point, this line, and this line, all right? Okay, so let's drive some equations from what we see, the mechanics. This is the mechanics of how's the cross section is behaving. All right, so if I want to derive the equation of d theta, like let's assume that this is a circle and this is the center of the circle and this is a curve on the circle. If this is C, is the radius of the circle. So if you want to find dl, dl is equal to C d theta, right? Multiply C by d theta. If you want to find it the other way, like if you want to say tan d theta is equal to the opposite, dl over C, but I said that d theta is very small angle, so we can't say d theta is equal to dl over C, so dl is going to be equal to C d theta. So either way is fine. All right, If you want to find the strain that happened in this beam here, what is the value of the strain here? Okay, let me ask, what is the value of the strain here?
In the middle?
In the middle.
Should be zero.
Zero stress, zero strain, because it didn't move anything. That's where the neutral line is. Once you go up, it is a compression strain. Once you go down, it's elongation strain. Okay? So the strain, what is the general rule of the strain? What over what? The elongation over the original distance, right? Like if you pull this pin and this pin moved the like dl, but it's the original line, the original distance is L, so it's dl over the original length. So epsilon is dl, the amount of compression over the distance, this distance which is dx that we got. So it's gonna be dl over dx. So if we want to substitute here, so and get this one here, like removing this, is gonna be dl is equal to epsilon dx. So epsilon dx is gonna be equal to c d theta. So if you want to find d theta, dx is gonna be equal to epsilon over c. That's the first equation that we need. And what is that? What is d theta by dx? That's exceed, right? D theta dx. We're gonna keep it like this, but let me remind you, do you guys know Young's modulus? It's, we use what symbol to represent Young's modulus? E, right? Okay, what is the value of Young's modulus?
Stress over strain.
Stress over strain, sigma over epsilon, right? So if I wanna say epsilon, so epsilon is gonna be equal to sigma over E. So let's remove this and say that d theta dx is equal to sigma over E, and we have another c here, okay? And also we can remove d theta dx because it's equal to d squared y dx. So this is gonna be d squared y dx squared equals sigma over EC. That is another important equation. So we got this. Okay, let me remind you with something else. Do you guys remember in mechanics, if I want the relationship between the moment and stresses, like if I want to know what is the value of sigma here. So right now I'm done with epsilon. If I want to get the value of sigma in terms of the moment on the cross section, like if this cross section has a moment m, this is how we got sigma actually. Start with the moment. Do you guys remember? Here's the sigma 0, right? Once I go up, sigma goes up. Definitely it's a function of the inertia of the cross section, right? Okay, so if you guys remember, if you want to know the sigma as a function in the moment, sigma was always equal to m over I multiplied by the distance that you are getting this from. So if you want to hear the distance is 0, if you want to hear distance, whatever, 1, 2, until you get to C, if I want to know what is the maximum stress that this cross section has. Okay, so sigma over C is equal to m over I. We call this, but I have, this rule is only valid if this is elastic behavior. If it's not elastic, it's not valid. Just, I want to make this clear. This is for elastic behavior. For elastic behavior, that I mean that this is a perfect linear. But if it's non-linear, this is not gonna work for elastic behavior. All right. Okay, so right now we have sigma over C equal m over I, and I have here sigma over C, so I can take out sigma over C and put m over I, so we are gonna find out that m over EI is equal to d squared y dx squared, and this is gonna take us to the moment is equal to the Young's modulus multiplied by the inertia, multiplied by the second derivative of the deflection with respect to x squared, which this equation we call is the basic let me write it here. The moment equal EI d squared y dx squared. The basic differential equation of the elastic curve of a beam. And why it's a differential equation? Because it has derivative. And it's a second degree differential equation because the derivative is second degree. So that's the very important equation that I told you at first that is very important. And this is actually the core or how to solve the double integration method. So let's see how we can use this equation to solve, like in the exam, if I told you solve using the double integration method, you have to use this equation. You can't use another method, okay? All right, let me use the other board and let me shift this one here. I don't have. So let's have an example. All right, this example, I'm asking you to calculate I have a simple beam, and I have a load, uniform load W, and this beam has a length L, and I'm asking you to drive the deflection, drive the slope and deflection for the simple beam, not only the deflection, I also need the slope. But I'm gonna tell you how if you have the deflection you can get the slope. Okay, drive the deflection, which is y, and slope, which is theta, for a simple beam. All right, let's find the solution. By the way, there's no numbers, okay? It's all symbols. And I'll give you any beam that has any W with any length. All right, to solve this, I give you some steps to do it. Like, let me write the steps actually. Let's put number 1, get the moment as a function of the beam load. Get the moment as a function in the beam load. Number 2, equate the moment with, that is the moment. I want to equate the moment with EI multiplied by d squared y dx squared. And number 3, integrate twice. Why should I integrate twice? Because this is d squared y dx, and I'm asking you for the deflection. If you integrate once, you are getting dy dx. If you integrated another one, you get y, which is the deflection. Okay? All right, so that's actually the general rule to solve any double integration method. Let's see how we can do it. First, how we can get the general value of the moment. Like, you guys may be trained to, like, oh, this has W, so I know that the bending moment is something like this, and it's positive, and the bending moment in the middle is W squared over 8. That's what we train at. But what if I want it general, like I want it here? Can you tell me what is the bending moment here? So to do this, we need to cut the beam here and see what is gonna happen. So you're gonna have the beam something like this, and I have my support here, and I took my cross section here, and this is load W. And once you cut in a cross section, all the internal forces need to show up. Like you're gonna have, for example, let's say a shear goes down and a moment going like this. This is me, M, and that's Q, when you cut in a cross section. Because if there is no internal force here, this is gonna fail. Okay, because what makes this section stable, that there is an internal forces that doesn't allow this to goes down. if the beam lost the shear here, it's gonna fall. Okay, so that's what the shear is making, right? Okay, so let's solve this beam. What we are interested at, we need to get the value of the moment here as a function of the distance x. Like I pick the distance x and I want to find what is the moment here. To do this, basically, or what you have to do, you need to get the reactions. You know that the reaction here is WL over 2, right? And here, WL over 2. So I know that there's a reaction here, WL over 2. And if I want to get the moment here, so it's going to be WL over 2 multiplied by x, and it's positive, minus W multiplied by x over 2, right? To get the bending moment at this cross section. So you have two forces. The reaction is making moment like this, and the load is making moment like this. So let's write the general equation. The general equation that the moment at this cross section is equal to WL over 2 multiplied by x minus W by x. W by x is going to give you what is the resultant of the load here. But if you want to get the moment that makes that this resultant is making, that's x over 2. So this is W x multiplied by x over 2. If you want to make sure that what you have is right, you can calculate the moment in the middle. So this is going to be WL over 2 multiplied by L over 2. So this is going to be WL squared over 4 minus WL over 2 by L over 2 over 2. So this is going to be WL squared over 8. 228. Okay, so you have WL squared over 4 minus WL squared over 8 is going to give you WL squared over 8, which is this one. Okay, so that's the general equation of the moment at the beam. So you can calculate the moment at any point. All right, so I got this. What is the next step? Equate the moment with EI. So what I'm going to do, I'm going to say that this is equal to EI d square y dx squared, and this is going to be equal to WL over 2 multiplied by x minus W x squared over 2. By the way, this beam can be a cantilever. Like if you have a cantilever like this and you have a load like this, what you have to do, maybe you make x from here and then get the moment here and see what is the W here. So basically it's going to be negative Wx multiplied by x over 2, and that's the moment here. W negative because it's a negative moment if you look at the sign convention, multiplied by x. That's the load, and this is multiplied by x over 2. Or if you want to calculate from the other side, that's fine, but you are going to have the momentary action inside the equation. Okay, here from the right side, and also you have load here. So whatever that works for you, you can go for it. All right? Okay, so let's focus on this. Right now I have this equation. I equated the moment with EI. What should I do next? Integrate twice. I need to integrate this. When I integrate this equation, you integrate the left-hand side and the right-hand side. So let's do the integration. And I integrate with respect to x. So what I'm gonna do, I'm gonna integrate EI d square y dx squared with respect to dx, and I'm gonna integrate the right-hand side, WL over 2 multiplied by x minus W x squared over 2, all integrated with respect to x. If I integrated this with respect to x, it's gonna be EI dy dx. So this is gonna go to the next degree, right? When I integrate d squared y, so it's gonna be dy dx. If I'm gonna integrate dy dx, it's gonna be y. If I integrate y, it's gonna be y squared, y cubed. This is how we go up. Okay, let's integrate this. Let's find out how you guys remember the integration. WL over 2x integrated with respect to x is gonna be
X,
WL over 4 multiplied by x squared minus, how about this one? Wx cubed over 6 plus C1, constant of the integration, right? Okay, let's integrate another time. Like I'm gonna integrate EI dy dx with respect to x And here I have WL over 4x squared minus WX cubed over 6 plus C1, and all this is gonna be integrated with respect to x. This one is gonna be, when I integrate dy dx,
Why?
y equal to WL over 8
Over 12.
12.
over,
12 is 3.
this is 3, right?
Yeah, 3 times 4 is.
Oh yeah, this is gonna be WX, this is gonna be 12. And this one, WX, 4 over 24 plus
C1x.
C1x plus C2, excellent. So that's after we integrate the second time. So right now, I got what he wants. He wants the deflection y and the slope theta. I have y here, and I have theta here. All what I have to do, I divide by EI. But I still have the constants of integration. I need to find them out. To find the constants of integration, find the constant of integration. Let's find them. We use the boundary conditions that we know about this beam. What do we know about this beam? In terms of deflection and slope. We know that the deflection here is 0. Is the slope 0 here?
No.
Why? Because when this beam deflects like this, it's gonna be something like this. So there's a slope here, and there's a slope here. But I know for sure that deflection here is 0 and deflection here is 0. What else do I know?
Slope in the middle and
The slope in the middle is 0 here. This beam here, the slope is 0. So the slope is maximum here and get decrease until it comes here and becomes 0. So the slope in the middle is 0. So I can write here that at x equals 0, y is equal to 0. And at x equal L, y is equal to 0. And at x equal L over 2, theta is equal to 0, which is dy dx. I can use actually these two, and that's gonna be enough, because I only have 2 unknowns, I need 2 boundary conditions. All right, at x equals 0, y equals 0, look at this equation. If I substitute with y equals 0, and this is 0, 0, 0, so C2 is gonna be equal to
0.
0. So that means that is gonna give us that C2 is equal to 0. All right, if x equal to L, it's gonna be a little bit difficult because I have to substitute with x equal to L. So I'm gonna have that EI multiplied by y, which is gonna be 0. Let's put it 0. All right, 0 equal to WL over 12 multiplied by L cubed minus WL to the power 4 over 24 plus C1 multiplied by L. So C1 is going to be equal to.
I have a question.
Sure.
On the integration, this constant C1 is a constant.
Constant.
Why do we have Cx is supposed to be constant since it's an integrate?
So when you integrate a constant, like let's say you integrate a constant with respect to dx, this is constant multiplied by 1, so this is going to be Cx. That's how you, when you integrate constants. Okay? When you integrate constant is going to be Cx. That's how you go into levels, like the same way. If you have x cubed, your differentiator is going to be x squared. X, and then it's going to be 1. X squared, x1. If you integrate 1, it's going to be x squared, x cubed. You got it? That's the basics of integration. All right, so C1 is going to be equal, after you do this, it's going to be equal to negative WL cubed over 24. All right, right now I got C1, C2, so I'm ready to write the functions of y and theta. So let's write the function of theta. So this is the equation of theta that I'm interested in. So what I'm gonna do, I'm gonna divide by EI and make dy dx alone. So you will find out that theta, which is dy dx, is gonna be equal to 1 over EI multiplied by WL over 4 x squared minus w x cubed over 6, and C1 is w L cubed over 24. That is theta. That's the equation of theta. The equation of y, same thing. I have here, this is y, I'm gonna divide by 1 over EI. And this is gonna be WL over 12 x cubed minus WX to the power 4 over 24 plus C, which is negative W L cubed over 24 and multiplied by x. Okay, so these are the two equations that I'm interested in. Let me box them here so that you don't get confused. That's theta and that is y. Alright? Because I don't have space, so I write them here, but that's what we are looking for. So what we did, we got the general equation of the moment, and then we equated with EI d squared y dx squared. Then I integrated once, and I got the slope. I integrated another time, and I got the deflection. Then I used the boundary condition to find C1 and C2. Once I found them, I have the general equation of the slope and the deflection. This is slope, which is theta, okay? So right now, if you wanna find, for example, the deflection at x equals 0, so you basically substitute here, x is 0, x is 0, x is 0, y is gonna be 0. If you wanna find the deflection at y, like if you wanna find, let's say, you wanna find y at x equal L over 2. So you go here, substitute with L over 2, you're gonna remove x, L over 2 cubed, L over 2 to the power 4, and L over 2. Once you do this, this is gonna be equal to, you guys remember, I think this is something, one of the things that you might stick in your head. This is gonna be 5 WL to the power 4 over 384 EI. Once you substitute here with L over 2 and make the math here, you will find out that y in the middle is equal to this value. Same thing, if you want to find theta at x equals 0, you can come here and substitute with theta equal to, if you want to find theta with x equal to 0, and then you will find out what is the value of theta at first. Is that clear? So it's basically these 3 steps. And if you got the first one right, and you know how to do integration, you will master this type of problems. Maybe you train yourself on doing a cantilever, okay? I believe that's the only, not the only, but I mean that's the simplest way, because if I give you something, maybe I can give you something, it's definitely gonna be determinant. Like if I get you one in the exam, I'm not gonna give you one that is very complex, but maybe you train yourself. For example, if you have like a beam like this, and there's a cantilever here, and there's a roller here, and it's B, not W. Or if in a simple beam that has B, and then here is gonna be B over 2, B over 2, you take a section here, you don't have even a uniform load. That's a very easy one, it's just a concentrated load. The integration is gonna be a piece of cake. Good. All right, so this is so far the double integration method. I solved one problem, but any problem is gonna be similar to this, using these 3 rules. Drag the bending moment as a function of the distance, equated with the EI and the second derivative, and then integrate twice. The second method that I want to discuss with you today is the double integration method, the conjugate beam. Conjugate beam, before I get to the conjugate beam, I need to make sure that you guys have some structure analysis basics. So we're gonna review something very quick. So I'm gonna review some basics about the simple beams and the relationship between the shear force, the load, shear force, and moment. Okay, so let's assume that I have a simple beam like this. And it has a uniform load W like this. You guys know how the shear force diagram look like? Do you guys know how it's, sorry, the bending moment? How about the shear force? If I wanna, and also let's also do the moment. Let me also do, I have P here, P, and I wanna draw shear. Okay. So if you have a B like this, what is the reaction here?
B over 2.
B over 2 and B over 2. Okay, that's the loads and the reactions. How about the shear? How's the shear here?
Goes up.
Up
B over 2.
until B over 2 and then constant, and then B is gonna get us down, and then we will go constant until B over 2 get us up like this. So this is B over 2, B over 2. How about the moment? What is the moment here?
0.
0. How about the moment here?
That's straight.
BL over 4. Like you get the moment here, BL over 2 multiplied by L over 2, so it's gonna be BL over 4. That is the moment. Okay, how about this one? This one, we all know, like the reaction is WL over 2 and WL over 2. And this is gonna be this, and this is gonna go linear, right? It's gonna go linear because let's say that this is one ton per meter, and I'm gonna go down, every 1 meter I go 1 ton down. So it's gonna be this, until it goes up WL over 2. The bending moment is gonna be curved, and we all know it's WL square over 8. What do you guys notice about this? There's a relationship between the load, the shear, and the moment. Do you guys know what are the relationship? So the load is constant. The load is uniform, like it's a constant, right? So the load is constant, the shear is first degree, linear, and the moment is second degree, parabolic curve, right? So it increases degree. Here, there is no load, there is 0 load. And then the shear start to become constant, and then the moment start to be linear. So you moved it from 0 load to constant shear to first degree bending moment. So it increases degree. So that's W constant, the degree linear, and then the moment. So there's definitely a relationship between them. Let's find out. Okay, let's take this beam and do anatomy to this beam. And it has whatever load, like any load. And I'm gonna take small piece of this beam. I'm gonna take it out. And this piece is like dx. I'm gonna take it out. This piece is dx. Once you cut in this cross section, we said if we cut in a cross sections, the internal forces is gonna show up. If you cut right hand side, so the right hand side internal forces is gonna show up. And here I cut also left, so both are gonna show up. And let's assume whatever the loads here, like let's say that this beam has a bunch of loads, whatever loads. And this loads is function in X. All right, whatever, any types of loads. And if I cut here, you guys remember the positive? Here, the shear is gonna show up and the moment is gonna show up. Also, on the other side, the moment and the shear are gonna show up. So we're gonna have shear here and we're gonna have moment here. But it's not supposed to be the same value of the moment here. Definitely, yeah. Well, since this is a very, very small difference, it's gonna be M. But also with dm, very, very variation in the moment. Like let's say that you are get to the shear here, and you are taking an infinitesimal section here. So the shear here is Q, and here is Q plus dQ, right? Same thing here, I'm gonna have M plus dN, and here is Q plus dQ. That is the difference in the shear between here and here. All right, so let's study the equilibrium of this section. So for this piece, like, let's say that I have my beam like this, all right? And I take part here, cut here, and take it out. What makes this part stable is the shear on the left and the shear on the right, and the moment on the left and the moment on the right. If they are not stabilizing each other, this section is gonna be unstable. Like, let's assume that this beam somehow got moisture and the concrete got cracks, and then they lost the shear. So definitely this section is not gonna be stable. So assuming that this is a stable structure, if we take this cross section out, the internal forces on the left and the right is stable each other. So we can say that sum Fy for this small section, let's assume that the positive is up, is equal to 0. So all the loads up and down, they are stabilizing each other. So I have Q is positive minus Q plus dQ, because it's going down, and I have WFX minus W multiplied by dx, because that's the distributed load, and this is the length of distribution, so multiply them by each other, so this is gonna be 0. So once you do this, the Q is gonna be gone with the other Q, so you are gonna have negative dQ minus W dx is equal to 0. So dQ is equal to negative W dx. So you can say that dQ dx is equal to negative W. Or you can integrate both sides and you can say that Q is equal to negative the integration W dx. That is very important equations. Same thing we can say about the moment. We can take the moment here or here. Anyway, let me take it here. Okay, sum of the moment, let's say that this is point O. Sum of the moment at point O is equal to 0, and I'm gonna assume that this is the positive direction. So the positive direction, this is M, is gonna be positive, and Q is gonna be positive multiplied by dx. This shear Q is gonna be multiplied by the arm dx. How about Q plus dQ? How much moment it does? 0, because it passed with O. All right. How about this one? This one is gonna be minus M plus dm. Do I have any other loads that makes moment on this section?
W.
Hmm?
W.
The W,
W.
right? How about you guys tell me, is it positive or negative? This W is going down, right?
Yeah.
And my moment positive is this way, so this is negative. What is the value of this moment? It's a distributed load.
W dx.
W dx is gonna give you the resultant,
Times
multiplied by
dx over 2.
dx over 2. All this should be equal to 0 if this section is stable. But dx is very, very small. Dx is very small. Like, let's just say it's 0.000001. What if we squared it? How much is gonna be? It's gonna be double, right? It's gonna be way, way smaller. So in this equation, we can say that d squared x is almost equal to 0. It's a very, very small. Like, imagine that you are doing some calculation and you have a number like 0.001, okay? And then you will just take this number. You're not gonna look at the numbers like 0.00000 another 5. You will just take the 1. So this is how we are having dx squared here. We're gonna make it equal to 0 because dx by dx is dx squared, and this is very, very close to 0. Here I have positive m and negative m. They are gonna cancel each other. So I'm gonna have q dx minus dm is equal to 0. So dm dx is gonna be equal to q, right? Or we can say that, like, let me do it another way. Let me put the dm here is equal to q dx. So you can integrate both sides, you can integrate this and this, and you can say that m is equal to the integration of q dx. Or you can say that dm dx is equal to q. So that is the set of equations that you need to know. All right, so what we learned from here is if you want to get the shear from the load, you have load W, and you want to get the shear. Shear is equal to the negative integration of W dx. If you integrate W with respect to the length of the beam, you are going to get the shear. And that makes sense because the load is constant. Once you integrate it, it's going to increase degree, right? And if you want to get the moment, you integrate the shear with respect to x. All right? And this is going to increase another degree. But what if you have the moment and you want to get the shear? Q is equal to dm dx. You differentiate. So once you differentiate, you lose degree. So let's say that this is x squared. You differentiate it, it's going to be x, linear. And when you differentiate it one more time, you are going to get the load. So here, the moment is x squared, x, and this is constant. You integrate the constant, you get x. You integrate the x, you are getting x squared. But if you differentiate the x squared, you are going to get the shear, which is linear, and you are going to get the constant load. All right? So that is the thing that I want to make sure before I get into the conjugate beam that you guys understand what is the relationship between the load, shear, and moment. Does anybody have any question? All right. Before I get into a conjugate beam, let me also, let me build on this, all right? I'm gonna build on this thing. Like you have a load, shear, and moment. If you wanna get the shear from the moment, you differentiate one more time, you get the load. Yeah, like differentiating this way. If you wanna integrate the load, you're gonna get the shear, integrate the moment, integrate the shear, you're gonna get the moment. Conjugate beam is kind of use this in a manipulation way to get the slope and deflection. Right now we didn't talk about slope and deflection. All this are internal forces. How this is going to help me to find y and theta. All right. If you look at the relationship between y, theta, and xc, d theta is dy dx, right? Xc is d theta dx, right? So if I differentiate y, I get theta. And if I differentiate theta, I get xc. If I integrate one time, I will get theta. If I integrate one time, I will get y. Same thing with the relationship between moment, shear, and load. Integrate or differentiate. So conjugate beam is using this thing to find the slope and the deflection. So what is the conjugate beam is doing? It tells you, if you want to find out what is the deflection for a simple beam or any beam, draw a bending moment diagram, this moment diagram, and use this moment as a load on a beam. Like here, this is the beam, all right? Write it in a different way. This is my beam. It has a load W, right? And when you draw the bending moment diagram, let me draw the positive going up. Like let me draw the positive moment up like this. You can put it up and down, whatever you would like, okay? But just make sure what is it positive or negative? My positive, I put positive like this, and that's the bending moment diagram. All right? So the conjugate beam, it tells you, conjugate means, I don't know, like we can describe it like, what is the definition of conjugate like in English? Conjugate means
Similar.
like brothers and sisters or something?
Similar.
Similar, okay. So the conjugate of this beam is that you put this bending moment as a load on a virtual beam, not a real beam, virtually, okay? So I'm gonna take this bending moment and put it as a load. It's not moment anymore, okay? So how it's gonna be load if it's positive? So I'm gonna make the load is going up, all right? So this is not a moment anymore. This is a load on the beam. And this load is equal to M, and we are gonna divide it by EI. Okay? So this is the moment, and I'm gonna put the moment over EI as a load. That's not the real load on the beam, but this is kind of a manipulation so that I can get the deflection. All right, if you know the bending moment on a beam and you put it as a load over EI, if you draw the shear force diagram of this beam and draw the bending moment diagram of this beam, so this bending moment diagram is the deflection and this shear is the slope. Do you guys understand this? How? Since we said that if we integrate the load, one time it's gonna be shear and one time it's gonna be moment. Same thing, if you get the shear, that means that's the integration of the load. So the shear, it means that we integrated. Look at this. What is M over EI?
The deflection.
Here, M over EI, D square Y, dx squared, right? So if I get the shear of this beam, that means that I integrated once. So this has become dy dx, so that is the slope. And if I integrate it another time, that is gonna be y, right? Here, integration, here, integration, right? Do you guys understand this? It's kinda a twisted way, but this is how we manipulate what we have and what is the relationship between the parameters to get with the conjugate beam. So conjugate beam is not a direct way, it's a virtual way, so that we can, using the relationship between y theta and xe and the relationship between load and shear and moment, so that we can find out the slope and the deflection easily. All right, so once you do this, you will find that the shear is gonna be like something like this. Since this is a second degree, by the way, this is second degree, so the shear is gonna be a third degree, something like this. And the moment is gonna be fourth degree, something like this. And that makes sense because the slope here is not zero. There's a value of the slope, but the deflection here is zero. So that is, so what I learned from this, I get the moment and I put the moment as a load on the beam, and then I get the shear of this moment and the moment of this load, which is already a moment before. And I know already that if I get the shear and the moment of this load, that means that this is the integration and this is another integration. So I integrated this, d squared y dx squared. So I integrated to get this one and I integrate to get this one. So I do it indirectly by drawing the bending moment and the shear force diagram. All right, so I'm gonna talk next time in detail about this method, but I just wanted to give you an introduction, how we do it. That's not everything. There's a way, we need to change the support, we need to change many things so that we can make the problem complete and solve it. So I'm gonna send you a video on how to solve the conjugate beam, and then you guys watch it, and we're gonna have a quiz. And when I meet you guys next week, on Thursday, maybe we revise this one and see if you guys have any problems while watching the videos, and then start a new topic, okay? Right, does anyone have any question?
Can you just elaborate more on the virtual? You said this is a virtual moment. Can you just explain a little bit more?
On the moment?
Yeah.
So what I basically did here, in the real problem, I give you a problem like this, or a cantilever or whatever, okay? And then all what you have to do is to draw the bending moment diagram. And to solve this problem using the conjugate beam problem, we construct a virtual beam. And we put the moment as a load on this beam and get the shear and get the moment. And since the moment, since we know already from varsity principles that the moment over EI is equal to d squared y over dx squared, that's what we already know, right? And I already have the moment, and EI is constant. Okay, so you have XC, right? This is XC, the moment. If you divide this bending moment diagram over EI, you got XC. If you integrate XC, which is d squared y dx squared, is gonna give you theta. And if you integrate theta, you're gonna get y, right? d squared y dx squared, and then dy dx, and then you get another one. So you do integrations. So what I did, I used this as a load, like I put it as a load for a virtual beam, and then I got the shear in the moment. Rather than doing the integration, which is a very tedious work and it needs lots of basics. So rather than getting into the integration, I just use my skills to draw the bending moment, knowing that how much load did this beam have. And once I draw the shear and moment, I know that the shear is theta and the moment is y for this virtual beam. So I didn't do the integration, but I did some drawing that gave us the same answer. All right? Okay, next time we're gonna do this maybe when you watch the videos and go home, so it's gonna be better, right? Okay, sounds good. See you guys next time.